Hello calculus students, we're going to be looking at improper integrals in this lesson. There's more than one type of improper integrals, so we're going to look at a couple issues today of things that can make an integral improper and deal with those different possibilities. So why is this integral improper? Why is this integral improper? Why are these non-normal integrals or finite limits of integration integrals? Well, because they have an infinite part in one of their limits of integration. These integrals, these first three, are all integrated from a constant or some finite place, and we're going and finding the area accumulated between that place all the way out to infinity. So you might tell yourself, well, of course those are all going to be either positive or negative infinite amounts of area. And what we're going to start looking at here as we get into the issue of infinity more deeply, especially in chapter 9 of series, is that sometimes these settle down to a finite value and sometimes they do what's called diverge and go off to infinity, as you might expect, but they don't always diverge. So let's look at a couple examples to begin with. So this is the area under the curve 1 over x from 1 to infinity. Just sketching what that might look like. You could look at your calculator, of course. But 1 over x is something we're familiar with. I want to just go from 1 to infinity on this function this time. 1 over x, of course, looks like this. I'm not interested in this branch of the rectangular hyperbola. I'm just interested from 1 to infinity, or in other words, this area. So you can see that it gets smaller and smaller and smaller. In other words, as I go out towards infinity, I'm accumulating less and less and less area. The only question is, does it get small enough, fast enough, to actually converge to some finite value, or does it just keep growing infinitely? That's going to be the theme of this whole next unit, is how fast things grow, how slow things grow, and do they get small enough, fast enough, do they get large enough, at what rate? That's going to be the key in series and improper integrals. So what's it going to be? Well, it's going to be infinity or not. Let's prove it. So the way that you do this is you realize that this limit is going up to infinity, and you say, well, I'm just going to use a limit here. I'm going to say that this is actually, I'll put it down here, equal to the limit, and you can call it whatever. Usually it's called b. As b approaches infinity, why did I use the letter b here? Because a to b. If this was infinity down here, which we'll do an example like that in a second, you might want to say as the limit as a approaches maybe negative infinity. We'll see some different possibilities. So I'm going to go from 1 to b of dx over x. So I've turned this into a limit problem because limits involve infinity, and that's how we've learned so far in this class to work with infinite quantities. So what does this integral actually evaluate to? Well, that part's easy. You guys know this integral. The integral of 1 over x is, of course, the natural log of x evaluated from the limit 1 to limit 2 with the fundamental theorem. So notice I haven't touched the limit at all yet. And now I'm going to use the fundamental theorem to say that's equal to big F of b minus big F of a. So what happens there is you want to simplify. So natural log of 1 is, of course, 0. So this is the limit as b approaches infinity of the natural log of b, because this guy goes to 0. So now you've got the natural log, and you're taking the value inside that natural log. Think of this as x, if you will. Don't make it overly complex. The limit of the natural log goes out to infinity. The natural log grows slowly, but it does indeed keep on growing. Just like thinking back to that picture, the area is growing slowly, but it does indeed keep on growing. The question is, do all areas work that way? The answer is no. We'll see if this one does the same kind of thing or if it settles down to some convergent value. This one, we'd say diverges. So we'd say this guy diverges to positive infinity. There's the proof. Okay, handling this guy the same way. I could look at the picture of e to the negative x and think about what kind of area is being accumulated. I'm just going to avoid that this time. So we're going to say the limit as this is equal to the limit as b approaches infinity of 0 to b of e to the negative x dx. Another easy integral. You're going to have some easy integrals and some that involve Calc 2 techniques like trig sub and partial fractions and all that business. So let's see, this is going to be then e to the negative x is negative e to the negative x for its antiderivative, evaluated from 0 to b. Notice I'm not touching the limit until the very end of my problem. So this is going to be negative, I'm going to factor that out. Let's see, e to the negative b minus e to the negative 0 is just 0. So that's going to be the limit as b approaches infinity of negative 1 over e to the b minus 1. Now I'm going to evaluate my limit and put it in at the end. So as b approaches infinity, this is 1 over something really large. So this is going to be negative 0 minus 1. 1 is just 1, that doesn't depend on b at all. So this is going to be equal to 1. So crazily enough, if you integrate this curve, e to the negative x from 0 to infinity, it doesn't keep getting bigger and bigger and bigger. The area actually accumulates and settles down to exactly 1. There's the proof. What's this problem actually look like? It doesn't look so dissimilar from the other one. E to the negative x is not a function you should really know, but it looks kind of like this. Oh yeah, it is. Never mind. Is it a function you should know? Yeah, it goes through 1. It's exponential decay because it's been flipped, right? So this area right here actually does settle down, and if you go all the way out to infinity, becomes 1. That's kind of a mind-boggling concept. We're going to see some different interesting applications and ways to get our head around that as we continue into this unit, but fun stuff is on the horizon, and you're kind of already there. So let's see, another one of those same kind of problems. This guy's going to then be the limit as b approaches infinity, again b because that's a to b. This guy's arctangent, isn't it? So arctangent of x, that's what that integrates to, from 0 to b, not touching my limit yet. So this is going to be the arctangent, oh my, I mixed notations. The arctangent of b minus the arctangent of 0. So this is going to be, what's the arctangent of 0 go to? This goes to 0. If you think about your tangent, tangent is 0 at 0. So this is going to be equal to, if I put b in the arctangent, ooh, good question. What's that look like? I think you have to think about what the graph of tangent looks like. So let's remember, tangent, plain old tangent, not arctangent, is trapped between pi over 2 and pi over 2 each way. So arctangent, remember, the inverse function in general takes that and flips it. Arctangent looks like this, if you remember, a little harder. But you should know from inverse functions that you change y and x, so arctangent is going to be a 45-degree rotation, which is going to lead to these values. So we're going to have negative pi over 2, it goes like this. So what is its limit as you approach infinity? That asymptote. This is equal to pi over 2. So the area that accumulates under this curve also settles down, or does what we call converge, to a finite value of pi over 2. These would be great examples to actually confirm with your calculator. Put this in y1. I pause the video right now and try that out. Put this in y1 and plug in bigger and bigger and bigger values for going out to infinity, and try math 9. Like try math 9 from 0 to 1,000 and see if it's close to pi over 2. Then try math 9 from 0 to 10,000 and see if you get closer to pi over 2. The area is supposed to converge to pi over 2 on this problem. Let's look at another example of this same kind of improper issue with our limits of integration being infinite, but let's change it from just infinite on the upper side. So here's another example. So this time we're going to go from negative infinity to infinity, so kind of infinite in each direction, of e to the 2x over 1 plus e to the 2x. Oh, let's go e to the x up here, my bad. There we go. Okay, that's the problem we want to do. So how do you do that guy? Well, you want to do what we've done with fundamental theorem problems in the past and split it up into two pieces. So find a finite spot that you'd like to split it at, like 0 of course, but you don't have to do it at 0. You could go 1 or 2 or whatever, and split it into two pieces. So we're going to go negative infinity up to 0 of the stuff, plus 0 to infinity of that same stuff. And we're just going to basically treat it as two separate problems. Now, of course, you could turn this integral around and go from 0 to negative infinity with that negative trick that we learned, but let's just go backwards. So this time we're going to say the limit as a approaches negative infinity from a to 0 of the stuff. And what we've been doing, b approaches infinity from 0 to that b value of that same stuff. So there we go, I'm going to switch back colors to black here. So now we just need to do those integrals separately. So it's the same integral that we're going to need to do. What does that integral actually become? Well, over here, I think you should think about doing a u substitution here. If we let, let's just think about, I'll write my substitution right here. Let's say u is e to the x. Then du is, of course, e to the x dx. So these are going to become, I'll try to stay color consistent, limit as a approaches negative infinity, not touching the limits until the end again, a 0, and let's see, maybe I should just resolve what the integral is over here first. So that's going to be du, there's du right there, and on the bottom I have 1 plus e to the 2x's e to the x squared. So that's u squared. So that guy is the arctangent of u, isn't it? So this guy over here is going to become, let's get rid of this right away, it's going to become the arctangent of u, u being e to the x, evaluated from a to 0. I'm just going to go like this. And then this other limit's still hanging out, still chilling. We've got the arctangent of e to the x there as well, evaluated from 0 to b. And we just need to do these problems. So I've got the limit as a approaches negative infinity. And you can show less work than this. I'm just being exclusive, very careful today. If I plug 0 in, I get the arctangent of 1. What's the arctangent of 1? That's pi over 4. Minus, if I plug a in, I'm going to have the inverse tangent of e to the a. And over here I'm going to have plus the limit as b approaches infinity. Maybe I should put some stuff around these. So if I put b in, then I'm going to have the inverse tangent of b there, minus the inverse tangent. If I put 0 in, I'm going to have the inverse tangent of 1 there. So what's this going to actually equal? So now we're going to actually do the limits. So this limit doesn't affect that pi over 4 at all, so that pi over 4 is coming out here because it doesn't have an a on it at all, right? It's just pi over 4 every time as we approach negative infinity. And then over here we have minus basically the inverse tangent, let's just like plug it in, of e to the negative infinity. So what's that going to be like? That's kind of like the inverse tangent of, you don't want to really write that, but of 1 over e to the infinity. What's 1 over e to the infinity? It's basically 0, right? So this is the inverse tangent of 0. Where is tangent 0? We did that earlier in the video. That's going to be 0. So far we've got pi over 4, and this guy goes to 0 as a approaches negative infinity. Then over here we have plus the limit as b approaches infinity. The inverse tangent of b, let's kind of just plug that in again. The inverse tangent of, we're approaching infinity this time. And that goes back to the picture we were just talking about a second ago. As you approach b on the graph of inverse tangent, which I know is one that you're not super familiar with likely, but you go to that asymptote value of positive pi over 2. So that's going to be plus pi over 2. And then this guy, inverse tangent of 1, is again pi over 4. When you take the limit as b approaches something, it doesn't have a b on it, so it's just minus pi over 4. So what do we get here? We got pi over 4 minus pi over 4. Those go away. 0 is 0. This limit converges to pi over 2. The area under that curve from all the way that way to all the way that way, the area that stacks up is actually equal to a finite number of pi over 2. So here's an example of a problem where we have the same improper issue with one of the limits of integration being infinite, but we might have to apply something like trig sub or partial fractions or something like that. So ask yourself, how do you do this actual integral first? So you might want to pause it and think about that, run through your list of advanced integration techniques. So we're going to be going the limit as b approaches infinity of the integral from 1 to b, because that's where the infinite part is. And we're going from 1, the area under the curve of that curve, from 1 to infinity, and seeing if it diverges, converges, or whatever. So we have what that integral is right here. Okay, so if you thought about it for a second, you should have come up with integration by parts is the way to do this problem. So let's do a u dv substitution. So what can we integrate? I think either thing we can integrate. I'm going to go for the e to the negative x. See what happens. So the integral of that is negative e to the negative x. So that leaves this part. Oh, should have put a dx there. To be u. So then du is just negative dx. So let's see what that becomes. Let's see. Let's just do the integral right here. So uv is going to be 1 minus x negative e to the negative x minus the integral of v, so minus minus is plus, du is another, I didn't put my v in there, minus the integral of v du, so there's a third negative which is going to make it back to negative. So that's going to be negative 1 minus x e to the negative x. And this is going to integrate the same way that that integrated. So we're going to get plus, because of that extra minus, e to the negative x, plus c. Let's see if we can simplify. I'm going to distribute here and see if we can collect any terms. So I've got minus 1 e to the negative x, plus x e to the negative x, plus e to the negative x, plus c. That and that are like terms, are they not? So these guys cancel out to 0 since they're equal and opposite. So I'm going to get x e to the negative x plus c. So that is the thing that we need to be integrating with during this process. So we have the limit still, haven't touched it. So this is equal to the limit as b approaches infinity. And that integrates by integration by parts to x e to the negative x. And now we've got limits from 1 to b. So now we're going to say, all right, so this is equal to the limit as b approaches infinity. Still not touching that limit. And I'm going to have b, e to the negative b is really just b over e to the b. I'm going to start rewriting things like that. We've seen it enough times. Minus, and then 1 is going to be 1. 1 there is going to be e to the 1. So what's that going to be as b approaches infinity? So this guy you could do with L'Hopital or with order of magnitude. Since we just worked with order of magnitude yesterday, I'm going to go with that. Which one of these functions grows faster as you approach infinity? Remember, you can only use that order of magnitude argument as you're growing towards infinity or actually decaying towards negative infinity, which we want to usually avoid. Maybe use L'Hopital on those ones too. Either way, you're going to get the thing in the bottom grows faster, so that's going to go to 0. And then over here, there's no b in there. The b approaching infinity doesn't affect it at all. So actually this is not a divergent integral, it's again a convergent integral. And the area under this curve, whatever this bad boy looks like, approaches negative e to the negative 1, or negative 1 over e, as you approach infinity. So for the final examples today, I wanted to consider a different variety of improper integral. So we so far just looked at improper integrals which involved infinite limits of integration on one or both sides, like that last problem, or a problem a second ago. So you can see that these two integrals up here don't have infinite limits of integration, but they're still considered improper. And here's the reason why. If you look at the graph of 1 over the cube root of x, it looks like this between 0 and 1. So whereas 1 on this side isn't an issue, you can see that this goes up to the edge of a vertical asymptote. In other words, that side is uncertain as to whether, if you actually find the area all the way up to that edge, like we're supposed to, 0 to 1, whether that's going to be infinite, convergent, or divergent. So you have to treat this as an improper integral as well. You might say, well, who cares? Like, isn't this not going to be an issue? I've done integrals all day like this one. I think that they've carefully avoided improper integrals, and I've done that all the way up to this point. So we'll see a sneaky one in a second involving this problem. Okay, so how do you do this then? Well, you turn it into a limit problem. Let's take the limit, and you can say a, b, whatever. As a approaches, what we're concerned about approaching here is not infinity, but over here approaching 0, and not just from either side. We're really concerned about approaching it from this side, so that's 0 from the right. And we're going to say that that then goes from a to 1 of the problem in question. So this is equal to the limit as a approaches 0 from the right of what? So remember, this is x to the negative 1/3 power, so we just need to apply our integration power rule to do the problem. So that's going to be x to the 2/3 power divided by 2/3 and evaluated from the limits that we have. So not touching the limit, just like on the other improper integrals that we just did. So now I'm going to stick those in with the fundamental theorem. I'm going to factor out the 3/2 first. So if I stick 1 in, any power of 1 is 1. So that's going to be 1, because I took the 3/2 out. And I've got minus a to the 2/3 there. So this is going to be, since that's a constant, I can even factor it outside the limit entirely. I'm going to do that. You don't have to, but it might be easier to think about. So now I've got the limit of 1 minus a to the 2/3 that we've got to deal with. So this is equal to 3/2 times what? Well, this doesn't involve a at all. It's not changing. It's just 1, 1, 1, 1, whether you're approaching 0 or infinity or whatever. So we're approaching 0, but oh well, that's going to be 1. So as we approach 0 from the right and we stick things into the 2/3 power, what's that going to be? Well, I think it's just going to be 0. You can basically just stick 0 in there and be done. That's just 2/3 power. So 0 to any power except for 0 or infinity, which are indeterminate, it's going to be 0. But this isn't that case. It's not indeterminate. 0 to the 2/3 power is 0. So this actually comes down to a convergent limit area value of 3/2. That's how much area you get when you integrate this curve from 0 to 1. If you go 0 to 2, you're probably going to get something else. Duh. Okay, so another equally simple problem. So 1 over x cubed. You should expect there to be a vertical asymptote at 0, because if you put 0 into this function, you break it. It's undefined at 0. There is, in fact, a vertical asymptote right here. Do you need to know exactly what it looks like? No. You just need to recognize that it has an asymptote on the edge of the integration. So let's do this problem. So we're going from 0 to 2. So we're going in, whatever this looks like. I don't know if it's similar to the other one. X cubed, I don't know, let's see, what does it look like? Yeah, 1 over x cubed I think kind of goes like this. So we're thinking about this area right up until that spot. So what is this equal to? It's equal to the limit as, let's say, a approaches 0 from the right again, because we're going up this way again. We don't need this piece down here. Of the integral from a to 2 of x to the negative 3 power. I'm going to write it like that because that's how we integrate it, right? So that's going to be equal to the limit as a approaches 0 from the right. Let me clean this up over here. Of, let's see, what's that integrate to? X to the negative 2 divided by negative 2 from a to 2. I'm going to clean that up a little more. That's the limit as a approaches 0 from the right of negative 1/2 with the x squared on the bottom. Okay, so what's that equal to? That's the limit as a approaches 0 from the right. Oh, excuse me, I'm going to factor the negative 1/2 out front, just like I did on that other one. So now we just have 1 over x squared. So we're going to go put the 2 in, so it's going to be 1 over 4 minus, this is negative 1/2 out in front, right? Minus 1 over a squared. So that's going to be equal to negative 1/2. Now let's do the limit finally. So this doesn't have an a in it, so it's still going to be 1/4. As we approach 0 from the right, what happens here? We're going to have 1 over like 0.00001 squared. So that's 1 over something small, and then when I square it, I think it's going to be even smaller. The idea is this is going to be really small on the bottom, so if I have 1 divided by something really, really small, I can cut that 1 up into a lot of pieces. In fact, if I make this thing even smaller, a lot more pieces. In fact, if I make it even smaller, it's an infinite number of pieces if I make it infinitely small. So this is minus infinity here. So what happens here is that we've got negative 1/8. Negative times negative is positive infinity, so plus infinity over 2. I don't think infinity cares about this 2. I don't think infinity cares about this negative 1/8. It's just infinity. This area, even though it looked really similar to that previous problem, is not convergent. It actually diverges. You have an infinite amount of area in this poor drawing that I have tried to do here. So this should really illustrate one of the pitfalls in integration, which is a big deal and which we've avoided completely until this point in class. Let me show you a really similar problem. What if you integrate from negative 1 to 2 of dx over x to the third? Well, what do you get for that? Well, it's pretty much the same problem as over here, right? So the antiderivative is negative 1 over 2, the x squared on the bottom. You go like this, right? Just Calc 1 type stuff, negative 1/2. You stick 2 in, you get 1/4, just like we did a second ago. This time I'm sticking negative 1 in, so minus negative 1 squared, like so. You get negative 1/2, 1/4. That squares the negative away, so it's just minus 1. So it's negative 1/2, 1/4 minus 1 is negative 3/4. Negative times negative is positive, so 3/8, right? That's how much area is under this curve from here at negative 1. That red plus that blue equals 3/8, right? Wrong! That's not true at all. Think about what we just developed. This is what you would have gotten in Calc 1 if you totally have ignored this issue of possible improperness with integrals. So I'd have never given you this problem in Calc 1 because you weren't ready for it. You'd never have seen it. So easy to get the wrong answer here. This is in fact an improper integral, and it's an improper integral of the sneaky sort because there's an asymptote in the middle of the integration. You can't just ignore that. The way you'd have to do this properly, and what's the right answer, by the way, because the right answer is not 3/8, is split it up. You'd have to split it up at that discontinuity, that asymptote. So that asymptote is at 0, so I need to split it at 0. If it had an asymptote over here at 3, and you're trying to integrate across that asymptote, you'd have to split it at that asymptote, or that discontinuity. So anyway, I have to do this plus, then from that asymptote to 2. I think this one might end up actually being finite. You'd have to do it. It'd be a good exercise for you to try. But this one we just did. This is plus infinity. So even if this guy is finite, adding it to infinity is going to yield what? Infinity. This integral has no finite value. This integral diverges. It has no finite area accumulation. So it diverges out to infinity. So I think that's good enough to do most of the assignment. We'll do some more examples together on Wednesday, but that should pretty much get you where you need to go. See you next time.